this example is a little bit more challenging. What if we take a wire that's not completely straight? What if it has a straight part and a curved part? How would we find the magnetic force on this loop of wire? So let's say that our wire is bent into the shape of a semicircle. It's got radius r. Let's label that on the picture. So from here to here is r. It forms a closed circuit, carries current I. The picture doesn't show us the current, so I'm just going to assume a direction of to the right on the bottom. And if it goes to the right down here, it comes up and curves around this way on the top. So there's our current I. The circuit lies in the xy plane, and there's a uniform magnetic field present along the positive y-axis. So this is our magnetic field vector, and x, y, and z look the usual way. So find the magnetic force on the straight portion of the wire and find the magnetic force on the curved portion of the wire. Let's start with the straight part because that one's a little bit easier. So on the straight part, the magnetic force is equal to I times L cross B. For this one, let's do out the cross product. We could do magnitude and direction. It'd be pretty easy to get direction. I cross B would give a force out of the page, but let's just do this one using the equation just to get a little bit of equation practice. So IL cross B, our current is I. Our length is the length of this wire. That's the diameter of the circle. So our length here is 2 times the radius. And the direction of the length will be in the positive, the x direction. So 2 times r times I, crossed with the magnetic field, which has a magnitude of B, and it points up, so in the j direction. Take our constants out front, we get 2 times I times r times b, I cross j, where I cross j is equal to k. So the force on the straight part is equal to 2 times I times r times b k hat. So that force on this part right here is out of the page, which is what we predicted with the right-hand rule. Now the curved part is not quite so simple, so let's do that next. On the curved part, our magnetic force in general is IL cross B. L is a vector, so it's a length and a direction. That's not constant. Right here L points up, now it's up and left. Here it's just to the left, here it's left and down, and here it's straight down, so L is not constant. So how can we deal with this if our length is not constant? Well, let's ask, could we pick a small piece of the wire, find the net force on that small piece, then find the net force on each small piece and add them up, and then that would give us the total force. Let's try that approach. So this small piece has a length ds, which points in the same direction as the current. So this little bit ds would make a small bit of force. And the net force would be the sum of all those little pieces. So now we've got a couple of choices. We can do the cross product, or we can do magnitude and direction. For this one, because the direction is changing, why don't we do magnitude and direction, where we'll get our direction with our right-hand rule. So let's try and think about that part first. Our thumb goes with the direction of the current, so always up around this way. Our B is the magnetic field points up, and then so points towards the top of the page. Hang on, I'm having a little trouble. Okay, there we go, got it. So ds, no matter what we do, comes along this way. B always points up, so our force is into the page. So right here, S is up, or right here, S is this way, B is this way, F is into the page. Come around here, ds, B into the page, ds, B into the page. So no matter which way we do it, that force is always into the page. So let's do magnitude and direction. The magnitude of the force is equal to the integral of the magnitude of the little bit of force, adding it all up, which is going to be the integral of current times the magnitude of ds cross B. What's the magnitude of a cross product? That would be the integral of I times the size of ds times B times the sine of the angle between them. And there's our angle theta right there. So here's how we're going to find the magnitude of our force. Let's see, we've got a sine theta here, but a ds here. Let's get on the same page there. You maybe remember from a high school geometry class that an arc length s is equal to radius times angle. That means a little bit of arc length ds is the radius times the little bit of angle it subtends. So let's put that bit in. FB equals the integral of I times r times d theta times b times sine theta. Now let's just make it look a little nicer. I is constant, r is constant, b is constant. Then we've got the integral of sine theta times d theta. We need to get our limits of the integral in there. So our first one happens when theta equals 0, and then we come all the way around the circle where theta equals pi. The integral of sine theta is minus cosine theta, and that's going to be evaluated at pi and 0. I don't think I have quite enough room on that line. I'll come down here. So we get I times r times b outside of minus cosine of pi minus a minus cosine of 0. Cosine of pi is minus 1. Cosine of 0 is 1. And that gives us 2. So minus and minus 1 is 1. Minus and minus gives us plus. 1 plus 1 is 2. Times I times r times b. We said that that force was out of the page, was into the page. So if we pick any value of ds with our b, we get into the page. So no matter where we do that right-hand rule, we get into the page. So the direction of our force, or our force vector with a direction then, is equal to minus 2I RB k hat. There's our net force, or there's our force on the curved part. The question doesn't ask, but let's just kind of think about this a little tiny bit further and ask what the implications of this are. So what we have is a curved part of the wire. The force on this part, right here, is 2I RB k hat. The force on this bit of the wire is minus 2 times r times b k hat. So one question you might ask is, what's the net force? Well, the net force is really easy to find. We just add up both those parts. What we get when we add those two guys together is 0. So the net force on this loop is actually 0. Another good follow-up question is, does it move? It's always kind of good to ask yourself these questions as you go through a problem. So if I look at this and I ask, does it move? Well, the net force is 0, so my first answer is no, of course it can't move, because F equals ma. If F is 0, then A is 0 and it can't move. So in one sense, that's true. I don't have a half a loop here. I'll just grab my phone as a thing. So this has a force that points out of the page here and into the page here. So if we ask what that force is going to do, I'm going to push down on this side and up on this side. It's actually going to rotate it. Okay, so we get a rotation. Now, a second ago, I just said, but it can't move because A is 0. The center of mass is the thing that doesn't move. So if F equals 0, if your net force is 0, it means you don't get any translation. An object won't go from here to here if your acceleration is 0. But if it just spins, then the center of mass stays still. There's no translation. Okay, so the answer to does it move is yes, you bet it moves. Okay, so the net force is 0, no translation. But the answer to does it move is yes, it rotates. And then if you were to ask the question, but if there's no force, how can it move? It's because the net torque is not zero. There. Now, we weren't due to get into that for another section or two. However, it's good to kind of think ahead and have a little preview of what's coming. Okay, in the next part, I think we'll do we'll start to talk about the net force on two different current carrying wires.